Hi there. My name's Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and in the last lecture of guitar amplification and effects, we looked at the effect of the coupling capacitors used to connect amplifier stages on the bass response. In this lecture, we're going to look at the effect of the cathode bypass capacitor on the bass response. Now, I'm doing all of this within the context of a common cathode amplifier, but the ideas could apply to other amplifier types. Now, the example I'm showing here actually has a bypass capacitor across the plate resistor as well. This has an effect on the treble response, so I'll talk about that in another lecture. This is actually a parameter in the fractal audio amp modeling simulation framework. So if you have an AX FX3 or FM9 or FM3, check back tomorrow and we'll talk about that. This lecture assumes you've seen my other lectures on the common cathode amplifier, but if you haven't watched those, stick around anyway and have some fun, and then go check out those earlier lectures, and then come back and watch this one again. This plate capacitor is typically pretty small, so compared to the other capacitors, it's going to have a pretty high impedance, and it mostly affects the treble, so we're going to ignore it in our calculations about the bass response. Now, in the last lecture, we focused on this coupling capacitor, and using the approximation methods of short circuit time constants for low frequency analysis, we shorted this cathode capacitor in order to focus on this coupling capacitor. In this lecture, we're going to go the other direction, and we'll focus on this bypass capacitor here, in which case, according to the SCTC method, we will short the coupling capacitor. That's convenient since for the rest of the lecture, I can replace RL in parallel with EL with a single resistance that I'll call R sub ACL. And then it will be very convenient to take all of this stuff down here and just call it some generic impedance Z. That's RKC, this resistor in series with the cathode capacitor, plus 1 over CKS, which is the impedance of the capacitor, in parallel with RK. So after explicitly writing out this parallel combination, the first thing we would want to do is multiply the numerator and the denominator by CKS to clear that out. And I wound up with something that looks like this, and this clearly is going to have the form of a shelving function. In this case, it's a high-pass shelf. Now, I tried rewriting this in several different ways. None of them were particularly more convenient than the other for what we need to use this expression for, which is to substitute it into a bigger, nastier expression later. So I'm just going to leave it like this. Now let's do some sanity checking on this expression. If I were to plug in j omega for S to get a frequency response, and then let omega go to infinity, which is what I mean by this notation, then this term here will go to 0, and I wind up with RK in parallel with RKC, which is clearly what I would have here if at high frequencies we imagine shorting out this capacitor. Similarly, let's think about what this impedance looks like at DC. Well, if S equals 0, then this factor winds up canceling out, and this factor winds up canceling out, and I just have RK times 1 over 1, which is RK. So here's the small signal circuit with this combined impedance ZK at the cathode. The AC here represents the small signal model of this triode, and as usual, we would like to avoid having to mess with the small signal model directly, so instead we use a Thevenin equivalent circuit we derived for looking down into the voltage-controlled voltage source that comprises the small signal tube model. As usual, the grid leak resistor here forms the input impedance of the amplifier, and really isn't important for the rest of our calculations here. So here we have the input voltage multiplied by mu, the amplification factor of the tube, and the whole structure is inverting, so there's a minus sign here. And remember from our Thevenin equivalent model for looking in plate side, this ZK looks like a bigger impedance. It gets multiplied by mu plus 1, when we're seeing it on the other side of the tube from the point of view of the plate side of the tube. But I have to be careful to remember RP, the dynamic plate resistance. And remember, this is a small signal quantity that depends on what the bias current is, and this isn't representing something like the resistance of the leads leading to the plate inside the tube. So, at this point in the class, the computation of the voltage transfer function should feel very familiar. We have the raw gain of the tube mu, but we don't see all of that voltage. We see it through a voltage divider. The voltage is being divided across this RACL, and in the denominator of the voltage division formula, we have these impedances in series. I almost said resistance, but I want to make sure I say impedance because I have this Z here. Now, remember what this impedance ZK looked like at super high frequencies and at 0. So the gain of this amplifier at a theoretically infinite high frequency looks like this, where we just put this parallel combination of RK and RKC in place of Z. And at a theoretical 0 frequency, the so-called DC case, we would replace ZK with just RK. Now, these are theoretical quantities that will give us expressions later that are easy to interpret. We know that the full circuit is going to have a coupling capacitor that's going to block DC, and we know that we'll never be able to pass super high frequencies in a realistic system because eventually parasitic capacitances would eat your lunch, although usually that's not too big of a deal as far as audio frequencies go. We'll look at this issue a little bit later. We're going to use this expression here to try to derive some expressions later that are easier to interpret in terms of time constants. So I took this expression for Z, plugged it in here in the expression for the transfer function, and then came up with this, and then I did a bunch of algebra. And that sound you hear is my YouTube watch time cratering. But don't click away. I promise this will converge to an interesting conclusion. First of all, in general, fractions within fractions make me sad. So I took this business down here and multiplied the numerator and the denominator of the big fraction by it. So that cleared that out, and I wound up with that quantity over here, and I wound up with that quantity multiplying this RACL plus RP, which is here, and then it wound up being cleared out of here for this term over there. I'm going through it in this level of detail because I'm hoping that if I did make a mistake in my algebra, that a kind viewer will find it. If you do find a mistake, let me know, and I'll put a correction in the description below and probably post a follow-up video. So here I have some terms that include S. Here I have something including S. Here I would have a constant term, and I would have a constant term from this. So I wanted to put all the terms with S together and all the terms that are constants with respect to S together, and that's what I did on the next line. So this is not particularly getting any simpler. Let me do a bit of spot checking. So I would have 1 times RACL plus RP, that's this. And then I would have mu plus 1 times RK times 1, which is this. So that's the constant terms. And what about the terms that have this CKS in them? So here's CKS. Well, I'll have mu plus 1 times RK, that's this. And then I'll have RK plus RKC times RACL plus RP, and that's this. So I think I've caught everything. If you see something I'm missing, let me know. So I clearly have some kind of shelving function. And something that caught my eye was that I have this expression here. And if I also then look at this RACL in the numerator, well, that looks familiar, especially when I include this minus mu. All of that looks like this. It looks like that theoretical DC gain A0. And that gives me a clue on how to proceed. What I did is I basically factored out this RACL plus RP plus mu plus 1 times RK term. So I wound up with RACL sitting in the numerator in front here. I then wound up with this RACL plus yada 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 out here. And now when you take this stuff out here and multiply it by 1, you get this original sequence here. But now to make the rest of this work, I had to put that sequence down here in the denominator of this subfraction. So when you multiply this through, this winds up canceling with this, giving you all of this mess in here. So let's take that expression and copy it to the top of the next slide. Admittedly, this does not look like it's getting any simpler, but the nice thing is I can now take this expression out here in front and rewrite that as just a 0. That's just a constant. It's the theoretical DC gain. And now I have something times s plus 1, something else times s plus 1. So I can now interpret this as a shelving function with time constants. I have a time constant associated with the 0, and I have a time constant associated with the pole. Come to think of it, in a couple of previous lectures, I've told my students that this lecture is the most complicated thing we'll look at all semester, and everything else after this will be easier. I could understand if they stop believing me now when I say things like that. Okay, the expression for the 0 at least is pretty nice. You add these resistances, you multiply by this capacitance, and you're good. That feels very natural. I do not have a good interpretation for what all of this mess down here is doing. If you can think of a good interpretation, please leave a comment below. Also, let me know if you know of any other derivations of this formula. I went through a bunch of web resources, and I went through a big stack of textbooks, some dating back to the 40s, and I could not find any place where anyone did this particular computation. That's why I went through this in such excruciating detail. I'm hoping that one of you can tell me that this derivation is right, or that it's wrong, and I'm really hoping that somebody can tell me somewhere to find this derivation, because I wasn't able to compare this result with any other sources. As far as I know, I'm the first person to do this computation, but that can't possibly be true. Now, this partially bypassed case where you have this RKC here isn't actually very common. It does appear in some guitar amplifiers, like in the Mesa Boogie dual rectifier that we've looked at a lot, so I do like to include it. But most of the time, they don't have an RKC here, and the cathode is fully bypassed. In that special case of RKC equals 0, this term, and this term disappear. So I do wind up with a simpler expression. The time constant for the 0 is just the cathode resistance times the cathode capacitance. And the time constant for the plate is a simpler expression. I still don't have a good interpretation for this, though. If you have one, let me know. And I should clarify a little bit. I think I've seen this expression for the time constant for the 0. What I have not seen is a derivation of the time constant for the pole, either in this more general case or in this more specific case. I have definitely seen people use this formula for designing. So let us again return to the Mesa Boogie dual rectifier, particularly the first preamp stage as our example. And here we have a capacitance of 1 microfarad at the cathode. RK is 1.8 kiloohm. RKC is 47 kiloohm in the case where this switch is not conducting. In the case where this light-dependent resistor being used as a switch is conducting, this 47 kiloohm resistor is bypassed, and then we have the fully bypassed case. That will give us higher gain. So, in the lower gain case, we add these two resistances at the cathode together, multiply it by that cathode capacitor, and we wind up with a time constant of something like 48.8 milliseconds. And if I take the reciprocal of that and divide by 2 pi to get an answer in hertz, I get a corner frequency for the 0 of 3.3 hertz. So that's well below any threshold of hearing that we are worried about in any way. Now, what about that higher gain setting? There, the main cathode resistance is included, but we don't have that RKE. So here we have a different story. We wind up with a time constant of like 1.8 milliseconds, and when I compute the corner frequency of the zero for that, I wind up with 88.4 hertz. Now that is interesting because the lowest note on a guitar in standard tuning, that low E, is 82 hertz. So this is playing a slight musical role in this higher gain setting. But this is just the corner frequency where the magnitude starts rising from the lower shelf. What about the actual low shelf and high shelf? So as far as the extremes of the shelf go, here specifically looking at the lower gain case in the Mesa Boogie, we use this formula with 1.7 in this RKAC spot, so that's the RK in parallel with RKE. And this 178.34 and the 72, these are numbers we computed in previous lectures. I was feeling a bit lazy, so I didn't write in the kiloohms here, but they cancel out anyway. Anyway, if I compute this value, I wound up with minus 42.3. And the thing is that the DC gain, which is the value of the lower shelf, well, that's not much different. I just put in 1.8 instead of 1.7, so that just gives me minus 41.3. So that capacitor is not very exciting from a frequency point of view, both from the standpoint of the relative height of the shelves and from the standpoint of the fact that that zero was at 3.3 hertz. Although to make that statement about it not being very interesting concrete, if I had a case where these gains were different, I would also have to really compute the pole frequency. I'll talk about that later. Now, what about the higher gain setting on the Mesa Boogie? Well, this DC value is going to stay the same, but in the higher gain setting, the cathode is completely bypassed. So this term goes away altogether, and I wind up with something like this. That low shelf gain is still 41.3. It's an inverting gain, which is why you have the minus sign there. But now the high shelf, well, that's now at an inverting gain of 71.2. So this is very different. And remember, the zero was at something like 88 hertz, which is now in a musical realm. So this does matter. Now, to complete the story, I really should compute the pole frequencies. I really don't want to. I just want to finish editing this video and go to bed. But, well, really, to complete the story, I should compute this. So let's go ahead and do it. I didn't prepare a slide for this, but I'll pull up Octave, which is this sort of open source version of MATLAB. Okay, let's write a script. I'm going to call it pain. Yes, I would like to create pain. All right, so let me strip all of this boilerplate out. We don't need that. Let's see. Let me make a variable top, and that's going to be the stuff in the numerator of the time constant. So I have RK plus RKC times RACL plus RP plus mu plus 1 times RK times RKC. All right, and then on the bottom, we're going to have RACL plus RP plus mu plus 1 times RK. All right, and then so the actual time constant, let's call it TP, is going to be top divided by bottom. And then to actually get the frequency associated with the pole, we'll take that and take its reciprocal, and we also need to multiply that by 2 pi down here in the denominator. Okay, so actually let me leave the semicolon off so it prints that. And now we need to put in the values. So RK was 1.8 kiloohm, RKC was 47 kiloohm, mu is 100, RP was 72, that's something we found out. Oh wait, I need to be careful, this is 72 kiloohm. All right, and then what about RACL? That's something we computed in a previous lecture under a bunch of assumptions that I'm using here. And let's see, that was 178.34 kiloohms. All right, so if I save all of that, I should be able to just actually copy and paste this and run it into the prompt window here. Let's see if that works. What? Oh, do you see my mistake? I always make this bug. All right, I forgot to multiply by the capacitance. So let's do that. So the capacitance, I'll just hard code it here. That's 1 microfarad. So let's try this again. Okay, so same thing. We'll just paste all of this in. Okay, so 3.3 hertz. Now, that's pretty much where the 0 was. Now the pole frequency should be higher than the 0 frequency. So to confirm that, I would probably want to go back and do a more careful job of computing the 0 frequency. That would be a good sanity check, but I don't feel like bothering because this case isn't very interesting anyway. Okay, so what about the pole location for the higher gain setting? So for that, I should be able to take this RKC and just set it to 0. So let's run this. And that gives me a pole frequency of 152.6 hertz. Remember, the 0 was at around 88 hertz, so that makes sense. The shelf runs from 88 to something around 153, so that's almost but not quite an octave. And now you see why I like to avoid improving in lectures and prefer to prepare things in advance. Anyway, thank you so much if you stuck it out this far.